So let's look at activity 3, sampling from car prices. Here are the prices of some cars at a used car showroom, and we looked at these prices earlier in this section, and they're not real prices. As I said then, these prices were generated for me by ChatGPT using some data I already had that I used with the Year 8 class, and extending it using some parameters that I set, that I wanted it not to have some sort of nice distribution, and I wanted it to be between these two values and so on. So we can do the same sort of thing with this data that we did with earlier pieces. So our objective here is to understand how random sampling can be used to estimate population parameters and to explore the variability of sample statistics. So what we've been doing. So we're going to be looking at things like standard error and so on. And we're going to be looking at the shape as we vary the value of n. Materials needed: the car price dataset, which was above, calculator, spreadsheet software or statistical tools, and as we'll see in the further investigation, I've used some Python to have a look at this as well. Our steps: part A, understand the population, so population description. The dataset contains the prices of 72 cars ranging from $3,000 to $12,950. The population parameters are that the mean price is $5,721.53. The standard deviation is $2,472.68. Then part B, we're going to do some random sampling. We're going to draw random samples and calculate means. Using a random number generator or otherwise, select samples of size 4, 9 and 16 from the dataset. As we've seen before, we've talked about this n equals 30 as being a bit of a magic number, but that's just for the exams. It's not really that much of a magic number. These samples are all of a smaller size than should give us good normality from such a distribution. However, we should see an improvement as we go from 4 to 9 to 16. And here you can see the samples. So my first sample of size 4 had a mean of 7,000. My first sample of size 9 had a mean of 5,627.78. My first sample of size 16 had a mean of $6,081.25. And you can see all the data there. And then at the bottom I've calculated the mean of all those samples of 4 and the standard deviation, the mean of all the samples of size 9 and the standard deviation, and the mean of all the samples of size 16 and the standard deviation. Compare sample statistics to population parameters. For each sample size, calculate the mean of the sample means across all samples and the standard deviation. So I've done that in the table, and we can take those values and we can compare them to the population values which were above. I'm probably going to do that just here. So compare these statistics to the population parameters. So there's the mean, and so if we do the sample of size 4, take away mu, let's take the modulus so we don't have to worry about negatives. The difference is 178.03. If we do the difference with those of size 9, it's 110.47, and with size 16 the difference was 30.78. So that actually works really well there, but there's no guarantee it will because of variability of samples. But we would expect to see this, that the larger sample would be closer to the mean than the size 9 and the size 4. It's just any individual one you take, it might not work that way. So this is what we would expect. As n increases, the gap to mu should decrease. Let's look at the standard deviation. If we do the population divided by SD4, it's 2.06. And remember, the sample there is size 4, So the square root is 2. That's really quite good. This one doesn't work quite as well because we would like to see a value of 3 there, 3.91. And if we do this one here, this is 4.59, and theoretically it should be 4. As n increases, the standard deviation decreases. So despite the fact that the values, this one's really close, despite the fact that these are not exactly what we see, we can see that the standard deviation is actually decreasing as we increase the size of the sample. And so if we move on to analyze and discuss results, visualize sampling variability. So we're going to here create the box plots or histograms of the sample means of each size using sensible intervals. Had to do a bit of jiggery pokery with the intervals to get them to work really well. It's worth keeping an eye on the values down here as we go across, and we can see size 4 here. Notice that the axis is less wide here, so we are moving in towards the middle value. And notice here also this particular set of 25 that I took actually is starting to look a bit more normal, isn't it, than the ones above, if we go back and have a look at those. But of course that will vary. We've seen that with other things, and obviously the sort of 10,000 sort of samples is going to help us a lot more with that. Observe how the variability of the sample means decreases as the sample size increases. We can see that the variability decreases both by looking at the standard deviations and the histograms, and that's the axis that I pointed out. So we've got a couple of discussion questions here. How do the sample means compare to the population mean as the sample size increases? As the sample size increases, the sample means tend to get closer to the population mean, and we saw that with those moduluses above. This occurs because larger samples are more likely to include a representative mix of values from the population, reducing the influence of extreme or unrepresentative values. The central limit theorem explains that as the sample size grows, the sampling distribution of the mean becomes more centered around the population mean. And this terminology here, sampling distribution of the mean, that's what we're looking at here. How do the means of these samples, how are those distributed? And the central limit theorem tells us that they should tend towards normalization. What happens to the variability of the sample means as the sample size increases? The variability of the sample means decreases as the sample size increases. When I talk about variability of the sample means, we're talking about standard deviation. Larger samples average out individual differences in the population, resulting in less fluctuation in the sample means. This reduction in variability is reflected in the decreasing standard deviation of the sample means, causing the distribution to become narrower and more tightly clustered around the population mean. Why is it important to take larger samples when estimating population parameters? Larger samples provide more accurate and reliable estimates of population parameters. They reduce the effect of outliers and extreme values, leading to sample statistics that better approximate the true population values. Additionally, larger values decrease the variability of the sample means, allowing for narrower confidence intervals, and we'll talk a lot more about confidence intervals in part 2 of this sampling, and more precise conclusions. This improves the robustness and validity of the estimation. Well, that's been fairly quick. Although it's quite a long video, hopefully it's given you some ideas about what's happening before we go on and look at the sort of theoretical model of these distributions, which is what you'll actually be examined on.